Okay, so in the last lecture, we talked about a theorem by Brouwer, which is the fixed point theorem, and we talked about the Borsuk-Ulam theorem. We also talked a little bit about path connectedness of two spaces, wherein if you have a space, path connectedness is that we can take 2 points, any 2 points inside the space or even on its boundary, and then connect them with a curve, and the curve will always stay inside the set. Okay. So if we split a set into two subsets, right, and say, well, those two subsets are, well, we take the union of both sets, and then that's the entire set. But they're separated, so there is a complement around it, or a space around those two spaces, or that one space wherein it's outside either of the spaces, and try to connect it. Well, it's not connected because there's going to be 2 points there. Where if we try to construct a curve between them, it ends up being outside the set. Okay. So yeah, that was the last lecture, and we also talked about some induced homomorphisms from the fundamental groups of certain spaces, and maybe some isomorphisms formed from that. So I'm going to continue, and we left off by saying that the n femboy sphere, Fsn, without one femboy, without a point in it, is contractible, and any curve that we embed inside it is homotopic to a non-injective map, which takes that point that we took away from it and sends it to some space containing that f to the minus 1 of x, which is inside the interval 0, 1, where we take our curves from. So I'm just going to continue what I was talking about there with a lemma. So this lemma corresponds with some fundamental groups and things like that. So let's start with that. So lemma. So okay, my marker. So if we phi sub I that maps x to y, let this be a class of homotopy or homotopy equivalence class, and let h that takes 1 to 0, or 0 to 1, and embeds it to y, be a curve with I being taken to the image phi I of x0. So I have a base femboy. Inside x here, and then I have another curve, or I have a fine line of femboys that we string up and line up together, and it's very, very fine, and it's infinitely fine, to be honest. So it ends up making a line rather than just a collection of points which are sequenced. Right, we have a curve. That's the curve that I'm talking about, and each I inside this 0 to 1 is taken to a certain curve, phi sub I, based at x. So all of these, x here is an element of any of these curves, not really based, as I mentioned in like a prototype of this lecture. Like I had a pre-recording and then I was interrupted, and then I had to restart. I said that it was all based at that point, but it's not really based on that point, or that it doesn't really start always at that femboy, right? At the same point. So not all of these curves start from the same femboy, but rather that femboy has a corresponding image or a corresponding femboy inside those curves or those lines of femboys, right? So we have a femboy that says, oh, you're almost like me, or like you're a transformed version of me inside that curve. So yeah, okay, so if I have that, then the diagram, so we start with the fundamental group of x based at 0. So this is not only a notation for, a femboy space which is, or a fundamental group of a space based at a femboid, but rather this is an entire entity in itself, which is called a base topological space, or base femboid topological space. Okay, so we have that, and it's taken to another pi 1 of y with a phi 1 of the base femboid. And we have a third fundamental group, phi 1 of y, based at the point phi 0 at the base femboid. So these base points here in these base topological space and these fundamental groups are not precisely the same. Okay, that's an important distinction to be made here. So there, and then another arrow here. This is by phi 1 star, and this is phi 0 star. And the mapping between this fundamental group and this fundamental group, B sub beta sub I, is an isomorphism. So this diagram commutes. So that diagram commutes. So now, the isomorphism, which is beta I, corresponds to the picture. I don't know if you guys can still see that. Okay, you guys can still see that. Corresponds to the picture. So I'll start with a point. And this point is phi sub 0 of the base femboid. Then I have a curve. And another point, phi 1 at the base femboid. And I have a loop that goes round and comes back to phi 1 x 0. So the flow goes like this and then like that. This curve here is h. Okay, as stated up here, this is the same as this segment. So the intuition behind this isomorphism is that we first travel along this line of femboids, and then we travel along this line of femboids, and then travel back. So first travel along here, travel round, and then travel back. Yeah. Okay, so following this lemma, so this here is just, this fundamental group taken to this fundamental group, so phi 1 star is just a regular homomorphism induced by the existence of both of these. And this map, phi sub 0 star, which takes this to this, is another induced homomorphism. But what makes beta sub I special is that it is an isomorphism between this fundamental group and this fundamental group. And one of the reasons why it's an isomorphism is that, well, it takes place in the same goddamn space, but we have two different base points inside that space. So I take one base point here, and all the curves are based around that point, or the space is based around that point. And then I have a copy of that same space, right? Same exact properties or same exact elements, right? Same exact femboids inside it, but this time I pick a different femboid to start it at. So, yeah, I start with the 0 femboid, the femboid located at 0, 0 for one space, and let's say in the second space I have another femboid that's based this time at 2, 2. Right? There is an isomorphism now between the fundamental groups of the first space and the second space. I can directly take this space and then send it to the other space seamlessly. Right? And that corresponds to this picture here. Okay. And yeah. Okay, so following this, let's have a proposition. if phi, so it's just one map this time, it takes x to y, is a homotopy equivalence. So homotopy equivalence, then there exists some map which is phi star that takes the fundamental group of the first space based at some point at some Femboy x0 and takes it to another space y, y here, based at the point phi of x0. Okay, so this map, this entire map, is an isomorphism. That's an isomorphism. Okay, so yeah. So I have a map that takes one space to another. It could just be a regular morphism, or it can be like a weird, strange transformation. It could be a homeomorphism. But nonetheless, if it's a homotopy equivalence, then there is an isomorphism between, one fundamental group of x here and a specific fundamental group of y based at the base point, which exists in x, transformed by this map. So essentially, yeah, the base point, it does exist in y because phi of x sub 0 is inside the image, or this image here, phi of the specific element of the image of this function phi of x0 exists inside y. That makes sense that, of course, the fundamental group will be based on that point. Okay, so now we have that isomorphism in this proposition out of the way. Let's move on to some preliminary things I need to introduce to you guys for notation before we move on to Van Kampen Theorem. Let's move this close so you guys can see it. So here's the proposition. Yeah, okay. So, yeah, here's some notation first before we start actually discussing the Van Kampen Theorem. Because the Van Kampen Theorem is a very important tool for constructing or calculating the fundamental groups of certain spaces. And we're also going to use it to construct the fundamental group of the circle and the torus in a different way than we originally first defined them to be or constructed them to be. So this is a more powerful tool than the first tools that we got, such as homotopy equivalence for constructing the fundamental groups. Okay. So let's introduce some notation. Some notation. If phi I is a homotopy, so just one homotopy, any homotopy inside the homotopy class. So phi is a homotopy and phi sub I of some base Femboy x0 is equal to some base Femboy in the second space y0 for all I. Then phi sub 0 star, as you remember from the last thing I mentioned, is equal to phi 1 star as maps. Okay. As maps we say so as maps phi 1 of x at base point 0 taken to phi 1, sorry, y based at y0, we say that this homotopy maps x 0 to y at y0 is base point preserving. And so the reason why we call it base point preserving is that well, we have one here that becomes the other base point. So I have a base femboy here in the first set x, and then under this homotopy, it is sent to y0, which is a femboy in this set. So when we have the ending, when we take the homotopy from this set, I mean not homotopy, but rather homomorphism from this group onto this group, we end up with one base point becoming the other base point, or one femboy becoming the other femboy, and not really deviating from what we set it out to be. So it is base point preserving. So we don't have any other base points rather than what we have seen here before, or what we have stated here. Okay, so let's jump right in to the Van Kampen theorem, which is a very powerful. I love this theorem. I think it's a new favorite. It's a new favorite theorem of mine. Now, I'm not going to go and prove it. There are many resources out there that can say on how you can prove this. But this is a really good tool of determining whether two spaces are really the same by constructing their fundamental groups. Okay. So the Van Kampen theorem. So this theorem states that if X is some set composed of two subsets A union B, so we decompose X, a space, into two sets, or rather just it's a space into two spaces A, B, with A, B open. So these two sets are open sets. So the base point x naught is inside the intersection between these two sets. And well, AB and their intersection is path connected. So you know the condition for path connectedness. So I split a ball open into two halves. And so on their own, what we're saying here is on their own, okay, not as one collection. A is path connected, B itself is path connected, and their intersection, so if I split the ball into two sort of ovals or ellipsoids, which kind of intersect when we put them back together to construct the original space, that small sliver of ellipsoid in the middle of both of them is also path connected. So if I draw a circle here and I bulge out this subset here and I bulge out this subset here, this is A, this is B. This small sliver here is A intersection B. So you notice that all of them are path connected because if I try to take 2 points in A and draw a squiggly line, it's inside the set. Draw a squiggly, draw 2 points, any points in B, draw a squiggly line between them, none of that, not outside the set. And same thing for A intersect B, draw a squiggly line inside it, and it's still inside the set. And I must state again, the reason why this doesn't fail under what we previously mentioned is because we are mentioning these guys as single sets themselves, so their own separate sets. We don't say that this is one set, okay? So that's the reason why all of these are path connected. So we go with that. So okay, we established that it's path connected. Then, but of course, this theorem fails when even though we split a set into multiple subsets that are path connected, or actually, if we split it into two sets, right, and take their intersection, and it's still not path connected, this theorem fails. Doesn't work. Okay. But we're really only concerned with the simplest of shapes when it comes to talking about algebraic geometry, so we won't have to worry much about spaces that are not path connected, whether we split them or not. Okay, so it's path connected. Then the fundamental group of this X at a base Femboy X0 is the free group. It's the free group, or free product, sorry, not free group. And we'll get to that when I'm done stating this theorem. Free product of pi 1 of A and pi 1 of B. If they are the image of the same elements, of the same elements, of pi 1 A intersection B. It's the fundamental group of their intersection. In other words, this here is homotopic to the free product of pi 1a and pi 1b mod some normal subgroup. So this will kind of require you to learn about, this is really where some of the deep knowledge in group theory comes into play when we talk about normal subgroups. Now I understand that I didn't discuss normal subgroups in Femboy theory. I think I'll just make a footnote about that. But that's another reason why I told you guys that these courses are very grueling and difficult, because we're talking about very deep topics in pure mathematics. So if you do have knowledge of group theory, good job, you understand this. So yeah. Or maybe maybe you're already viewing this video and thinking, what? You already discussed normal subgroups. What are you talking about? I'm saying, yeah, it's just before I did that. Okay. So I was talking in the time where I didn't do it. So yeah, okay. So this is the Kampen Theorem. So what we're doing is decomposing a space, right? Instead of trying to compute the fundamental group of a space using cell complexes and identification spaces, what we're going to do is split the space, right? Because when we're doing identification space and finding the fundamental group of those, identification spaces, which results in us finding out the fundamental group of a space that they become when we identify the edges, instead of doing that and thinking of it as one space, instead we're going to take two spaces, right, which are subspaces of that, and then their intersection, and then we find the fundamental groups of those intersections, and then say, okay, the union of all of these becomes that, fundamental group of that space. So if the space you're dealing with is difficult, think about splitting it in half and then finding the fundamental groups of those two and their intersection. Of course, in those two subspaces overlap a bit. So, yeah. So, restating what I said a while ago here in Femboy lingo, if I have two Femboys here in set A, and grab a bunch of Femboys and then pack them all finely into a fine line and connect these 2 points using that line of Femboys, all of the Femboys stay inside here. Okay? And same thing, B and then intersection of A and B. Okay. Okay, so now we talk about the Kampen theorem. Let's go on about and talk about free products. Now, when you think about the word free, you're already screaming, oh, free groups, right? Free groups. You know, words, letters, yeah, generators, yeah. That's what we're gonna talk about today. Okay, so the free product. If G1 and G2 are groups, so we're not just talking about collections of objects, but a set equipped with a binary operation that is associative, and each element has an inverse, but not necessarily commutative. Because if it's commutative, it is abelian. If it isn't commutative, it's not abelian. Okay, so groups. Their free product. Their free product, which we denote G1 star G2 or G1 asterisk G2, consists of words. So we abstract the notion of a femboy as a letter this time. Now, this is not to say that femboys are objects, but abstraction. We're abstracting them into some symbol, right? And then we put those symbols together. Those are words. So this does not necessarily mean we're multiplying them or whatever. We're just literally putting them together. String concatenation, like we discussed in FEM, episode 11, I think. So literal string concatenation, but we put some asterisk in between them. Quote unquote words, which is G1, asterisk G2, asterisk, asterisk Gn. With each Gi inside either G1 or G2. So this V here is just saying or, okay? I can just write it or here. Or G2. So any of these guys can be, you know, from G1. So we can say that this femboy is inside G1, this femboy is inside G2, and then G3 is inside G2. Small G4 is inside G1, Gn could be in 1. So that's it. Not inside their union, not inside their intersection, just inside the sets themselves. Okay, or the groups themselves. Okay. So yeah. So the operation, of course, for this is the star here, and the operation in these groups could be concatenation, or any the binary operator that we defined, such that of course it's associative and every element has an inverse, such that when we compose them, there's an identity. So obviously, you can already tell that from these being groups, they have an identity. For each of them, and that's going to be kind of important when we think about reducing these words and simplifying them. Because what if I have something like G1, G2, G1, G2? What if I have this word here inside the free product? Or sorry, G1 star. Star G2. What if I have this here? Well, of course, we can reduce it, right? Well, that's what we tend to find out with this criteria. Okay. So, they can be reduced in two conditions. I'm going to erase this. Words can be reduced, or we can reduce a word by, so the first one, So there are mainly two ways of decomposing words. If two letters I'll call them GI and GI plus 1. Two letters GI and GI plus 1 are in the same group. So if that is the case, then we can say that GI, if they're in the same group, we can remove that asterisk and just simply put them together. Then GI star GI plus 1 implies becomes GI plus 1. So in the long string of letters, if two elements beside each other or maybe separate from each other are in the same group, we can just literally put them together or remove the asterisk. Okay. Then 2, remove the identity from each group or either group. So as I said a while ago, since these guys are groups, obviously they have an identity, right? So remove the identity. So if I have a string, or if I have a word, right? G1 star dot 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 star identity of G, of big G. G1 or 2 star dot 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 star GN. Then I can remove this identity and just say so I'll just say this becomes G1 star dot 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 star GN. In this case, yields a group wherein the identity is just the empty word. So the identity now is just the empty word. So if we try composing these guys together, we just get 1 or 0 or however which way you interpret it, or the base Femboy. Okay. Okay, so the second case here yields a group with the identity word, or the empty word as its identity. Okay. So you string up these Femboys together, and we have an identity Femboy, such that when we compose an element, right, one Femboy and its inverse Femboy, we get this identity Femboy, right? So I have a Femboy that prefers guys, and then I have the same exact Femboy, but he prefers girls, right? If I compose them together, I get the asexual Femboy, which is the identity for that space. Or say I have a masculine guy, I have a feminine guy, right? I have a feminine and a masculine guy, two polar opposites of each other, but same exact elements in other cases or in other descriptions. Compose them together, we get the androgynous person. That's the identity for that space. Well, assuming that both these guys are inside a group. And putting those together is the empty word. Okay. So here's some key properties. Here's some key properties of this kind of the free product. Okay. I'm not gonna list down the list. I'm just gonna list them down right here. So it's up to you guys if you guys want to just jot this down, or if you guys want to put it in a list. So some key properties. So the first property is that G1 can be embedded in this free product. And likewise, G2 can be embedded into this free product. And to do this first one, when we embed G1 in G1 star G2, what we do is just replace the identity. So we replace the identity in this new group with an element in G1, any element, or any femboy here. I know it skewers the perspective of what you'd have on that group for a moment, but this is really how it is. This is really a property. Okay, and to embed G2 into this free product, what we do is just replace the identity here with an element from this group, just like G1. So that's the first property. So the second property, if H is another group, and I have a class of morphisms, or homomorphisms, I think. Yeah, that takes any one of these, either G1 and G2, and takes them to H. It could be an isomorphism. It could just be a homomorphism. Then there exists a big psi or big phi that takes the free product between G1 and G2 and takes them to H, extending phi, phi 1 and phi 2. So an example, the big psi or big phi of this string asterisk Gn is precisely phi of L of 1 of G1 star star phi of L of n Gn, where L of n, or L of I, indexed by the letter I, not n, because n's the ending one here, okay, is equal to 1, 2, so 1 for this element, or this femboy, belonging in G sub 1, and 2 for if the element exists or belongs in G2. So this is just more indexing and then stuff like that, and modifying the abstraction for the femboys. In fact, you'll see that. Okay, so if I have a string, if I have the word G1, G3, G2, wherein G1 is inside capital G1, G3 is inside capital G1, and G2 is inside capital G2. This string, if we, asterisk it. So all of these guys are inside the free product, right? So so this becomes, so I'm gonna make phi of this, so this becomes, under the transformation, I believe this becomes 1, 1, 2. So we can index it. It's another way of indexing it or transforming it. And yeah, that's an example of, that's another property of free groups. So that's it. I mean, free products. Sorry, I keep saying free groups. The free group is just, these words, the concept of putting these together. But this time, free groups are, those words, right, put into one set, all possible words, over an amount of generators. And then, of course, the operation is concatenation, right? And that's, the free group's going to be important, okay? And it's a relatively simple. It's basically a group. It can be non-abelian or abelian, as long as, well, this time the operation is concatenation. Okay, so it has a specific operation, and the elements inside the underlying set of a free group are words over certain generators. And you'll see me use a notation that I've used before for conditional objects, like certain functions or types of curves, but this time in the context of groups. and they're called group presentations. Not representations, as we would discuss in painting, in abstract painting, but we're talking about presentations, like a way of describing the group. You know, by not just saying, you know, we have this underline set, we have this binary operator, and then put them, equip them together. That's just one way of presenting a group. There's other ways of presenting groups. Okay, so we'll get to that in a moment. So now, let's continue where we left off from Van Kampen. So, if I let C be that intersection between A and B. So, we don't want to clutter up things when we're talking about, you know, actually constructing these things, because in today's lecture, we will spend the remaining time constructing fundamental groups of certain spaces. So, yeah, we're going to use Van Kampen's theorem to find it and also prove that some of these are true, like how the fundamental group of S1 is the integers, and the fundamental group of the n torus, or the n femboy torus, is exactly z to the n. And we'll also show that the fundamental group of a genus 2 surface, so a femboy donut stuck with another femboy donut, glued along, you know, a subset or a disk we took away from each one, is z to the 4 when we abelianize it. So we'll get to that in a moment. Okay. So let's see the intersection between A and B. So C, we take C to A, we take C to B, and then there is another set X, which A and B are originally part of. Okay, and then we have 4 morphisms. I1, I1, I2, I2. So this mapping diagram commutes, and it implies the same thing holds for their fundamental groups, that between these 4 spaces, you know, there is some homomorphisms or isomorphisms between their fundamental groups. And that is precisely this commutative diagram. One of C at x naught. So they're all based at the femboy x naught. Then I have another one, pi 1 of A at x naught, pi 1 at B at x naught, and pi 1 of x at x naught. Same flow, but this time you have I1 star, or and then I2 star. There. So this implies this diagram. Because it would be too tedious to write out every single map on its own as like a bunch of lines. Although I can do that, it's much more better to visualize if we use a mapping diagram or commutative diagram. So, okay. So, first, before we continue further, okay, I'm assuming you guys already know about normal subgroups, okay? At the beginning of the course, I already implied that you guys are going to need group theory for this. So, I'm already assuming you guys know about normal subgroups, okay? So, we're just going to jump right in and find these things, assuming you guys know about normal subgroups. They're just they're just groups containing cosets of the underlying set, and then there's commutator stuff, and then other stuff like that. I'll just revisit that here. Hold on, just a minute. Yep. Yeah, an invariant subgroup of a group under conjugation. And normal subgroups are only where you can do mod stuff. So Z mod something P, that is in fact a good representation of normal subgroups. So mod P is a normal subgroup of Z. So we can take the quotient group of those two. So the thing you see a lot in mathematics, like Z mod P, or Z mod ZP, or as called Z mod P. And this is related. Mod ZP, B, and P, and mod P are normal subgroups of Z. This is getting very abstract, but this is really mathematics in the purest of levels. So if you're quite new to pure mathematics, this may become a little nauseating, but nonetheless, when everything clicks, it's a bunch of euphoria. You feel a bunch of euphoria when everything clicks together. Okay. So let's carry on. Is really copied this or took note of it. So let's erase this. Let n be the smallest normal subgroup So of x or pi. Oh, sorry. Yeah, pi. Sorry. Pi 1 of a based at x naught asterisk or star on b based at x naught. So this is a group. The free group or the free product between these two groups is also a group, and n is the smallest normal subgroup of that free product. Okay, containing I1 star of a certain curve gamma and I2 star of the same curve gamma. So to the minus 1 for all gamma. For all gamma inside pi 1 of C based at the point x naught or the Femboy x naught. Okay. Van Kampen tells us that finally, here's the most important fact. Van Kampen tells us that the fundamental group of x based at x naught is isomorphic. It is isomorphic to the fundamental group of A based at x naught. Star or the free product between A or the fundamental group of A and B based at x naught mod n. So this is the most important fact you guys need to know before we actually start constructing fundamental groups using Van Kampen. This fundamental fact, and this is the favorite. This is one of my favorite formulae right now. It is my favorite. That the fact is that we can decompose the fundamental group of a space, or we can define or say that the fundamental groups of a constituent or constituents of a space is isomorphic to the entire or the fundamental group of the entire space. Or rather, it's the free product of the fundamental groups of these constituents mod the smallest normal subgroup of this product, containing such two curves here, or such two curves under a transformation, which are part of the fundamental group of the intersection between these two. So transform a line of femboys, which are part of the fundamental group of C, or the intersection between these two subsets, these two bulging subsets of femboys, of this entire set. And then mod that out from the free product of these two fundamental groups, and you got yourself the fundamental group of the entire set. And frankly, it's amazing. A really, really cool fact. And it's very useful as well. Extremely useful. And this is the tool we've been talking about, or that I've been alluding to this entire lecture. Now we're not going to stop just yet. I could go on about talking about push-outs, but I'll reserve that for a footnote. Okay, so let's use Van Kampen. Let's actually start applying this. Yeah, no, this is already like on the 4th lecture or the 5th lecture, and we're already talking about Van Kampen. Okay, so let's use Van Kampen to construct a fundamental group. So let's start with a bouquet of circles. So example. So X is a bouquet of circles, S1 or S1, which is defined to be S1 glued to S1. So S1 1 glued to S1 2 at some point x1 identified to a point x2. With that, this is an element of that. Yeah. So we can visualize this as this landscape type thing, and this is x1 identified with x2. So two femboys from these two femboy circles. Oh, actually, let's make it femboy circles. Fs1 and Fs1. So a bouquet of femboys. How romantic. Extremely romantic. So you have a bouquet of femboys that you want to give to your boyfriend or your girlfriend. How romantic, very romantic. Okay. If I'm not going to get sidetracked further, let's split this off into 3 subsets. So this becomes sort of prop 2 symbol to prop 2 symbols, but not precisely prop 2 symbols. So now we have A, we have the space A and the space B. Okay. And well, this implies that C is this little X pattern here. C is the pattern here. So I'm gonna cut this off here. So this section here, this section onto this section is B. This section to this section is B, and then this middle section here is C. Okay, so you'll notice now that all of these guys are path connected. Now I'm not talking about the space that they enclose, but themselves here. As I stated, S1 is not precisely the space that it encloses, but the boundary of that space that it encloses. B1 is the area enclosed by this curve. S1 is the curve itself. Okay, you notice that yes, they are path connected on their own. There are no breaks like that. And again, we're talking about these guys as their own separate sets, not as one set. So they are path connected. So A, B, C, path connected. And I'll demonstrate that. So take 2 points here, 1 point here, 1 point here, and then there, make a curve, single linear curve, and they connect seamlessly. Now you may be asking, okay, what about, okay, Smarty Pants, what if I take a point here, or a femboy here, and a femboy here, and connect them? Well, it's outside the set, isn't it? So that means it is, it's not path connected. Well, the thing is, here's the thing. the thing here, or the object here, exists in one dimension. Or it's a curve. It's a one-dimensional object. So the space inside it doesn't matter. And this cannot exist. Frankly speaking, this cannot exist. Only curves along it exist. So if I'm going to construct a curve inside here, it can only exist along it. It cannot exist outside it. Because that would mean that the image is outside the set. And that doesn't make sense. Like, imagine taking something from one set and then taking it to another set, and then that's not part of it. So imagine imagine having a function from R to R, but for some reason the function takes 1 to I, right? Doesn't make sense. Right? It's outside the set, so you can't make that. You can't do that. Especially if you want it to be a nice clean function. You can't make something like this. So it really stays on the boundary, and it is path connected. Because all possible curves we can construct that's part of this set, as we want them to be, if we ever want to show path connectedness, is always inside the set. Or it's always inside the curve. Okay, so if I'm not going to sidetrack myself further, these are path connected. A, B, and C are path connected. So, because they're path connected, this situation qualifies for us to use Van Kampen. Of course, when neither of these spaces are path connected, of course we can't use Van Kampen. Okay? Hate to break it to you, but if your space is too complex to the point we're in, none of them is path connected when we split into 3 sets. Sorry, bud. You're gonna have to use a more powerful tool than this. Okay. So they're path connected. So pi1 of x is isomorphic to, as we said a while ago, pi1 of A, free product pi1 of B. Now we're not picking a base point, so we're just using the fundamental group independent of the base point. Mod that normal subgroup N. Yeah. Now notice that C is contractible to this point here. So we can take all of C and compress it onto this here. So we can take all of these points along X and then just squish it onto that single point. And I said this before, I believe that if your space is contractible, its fundamental group is 1. And yeah, and we stated a while ago that N is the smallest normal subgroup of these two. And that could be C in most situations. So you'll notice that, yeah, C is a subset of these two. And if we make fundamental groups of these two, the fundamental group of C here could very well be N. Because look, it's small. C is small here. It could in fact be the smallest normal subgroup that could be part of both of these guys. Because it is literally the intersection of both of them. So C could very well be N. In this case, at least. And so N is 1. Because C is contractible to this point inside it, N is equal to 1. So we're just modding out 1. We're just taking out 1. Not really taking out, but modding out 1. Hence, pi1 of x is isomorphic to Z2. It's isomorphic to Z2, or rather, the free product between Z with itself, which is equal to a free group over 2 generators A, B, which are integers. And this is where the concept of free groups become important, because we notice we have 2 inputs now, right? And they are essentially the fundamental group, and they're groups, or where they come from, they're groups. So we form a free group over it. And because it's two elements, it's abelian already. We can make it strictly abelian and there wouldn't be any caveats here. So it's abelian also. Okay. So this is we can say that this isn't abelian. Okay. But if you want, you can make it abelian. So this is it. We noticed and you also notice, yeah, A and B here are simply just integers. A and B here are S1. And you notice that S1, or the fundamental group of S1, is the integers. So I'll note it up here. Notice A and B here, they are homeomorphic to S1. And S1, or the fundamental group of S1, is homeomorphic to Z, or FZ. All femboys represented, or any femboy, maybe location or maybe characteristic, assigned using elements of Z. So FZ, and then this is pi1. Pi1 of Fs1. So this is Fz. This is Fz. So we're just femboyizing things, if that's how you'd like to call it. Femboying things. It's like normalization or abelianization, but with femboys. So we make it such that it's in the context of femboys. So we just femboyized or femboyed. We femboyed these spaces. Okay, so that's one example. A bouquet of femboys. Very romantic. So example 2. Let's bump it up a notch. And say we want to find the fundamental group of the n femboy sphere, FSF. Actually, for simplicity's sake, let's first find the fundamental group of these spaces, then femboy it, or femboyize it. Okay, so EX2. So Sn. And then we can think of Sn, of course, as like a ball with the points. This is the equator. And we don't want to focus on the center. Now, A is going to be a slight bulge here. If I make it like this, slight bulge from the equator. This is A, this section. And we make another slight bulge on the equator. So it's like a dome with a small bulge on top. This here is B. And of course, the intersection of A and B is that small ellipsoid between them that contains the equator. So C, which is A intersection B, is this ring around the equator, or frustrum, or how would you call it? So ring around the equator, or frustrum, or section of it around the equator. My dog's barking. Excuse me. Okay. So you notice now, of course, these guys are path connected. Yes, they are path connected because take a curve here or take a point here, another point here, femboy here. Connect them with a line of fine femboys or fine line of femboys inside the set. So, yippee! They are path connected, so we can use Kampen. Okay. So you'll notice that A and B are convex subsets of Rn. So these guys are homeomorphic to an n disk. Now, these guys can be envisioned as a sphere or one three-dimensional objects, right? This is only the three-dimensional case here, though it kind of generalizes to n space. So keep in mind that this is a hypersurface, okay? It's a generalized surface. It's not precisely a sphere. and that is not precisely a cylinder around it, or a hollow cylinder around it, or a hollow ring around it. I don't say ring because ring already has a purpose in pure mathematics. It's not a geometric object, but an abstract structure. Okay. So you'll notice that A and B are homeomorphic. So this sign now is denoting homeomorphism, not isomorphism or like that. It's a homeomorphism for now. It's homeomorphic to the N disk, which is a subset of Rn. And that's convexity. Yes. So you notice from the last lecture that convex subsets of Rn have the trivial fundamental group. So 0 from the last lecture or the previous lectures. If I can find that. Yeah, excuse me for I'm trying to find it in my notes here. Well, either way, I already stated that fact that if it's a convex subset, 2 points connect them inside the set, or pass through the center, geometric center, the centroid of the shape. It has the trivial group. Okay. So yeah. And yeah. But the thing is, it's not precisely 0 in this case, but 1. Because our operation, when it comes to these things, is sort of like multiplication, right? So our identity this time, so the trivial subgroup, or the trivial group that everything goes to, or is homeomorphic to, or is isomorphic to, is 1, not 0 in this case. So pi 1 of A is isomorphic to pi 1 of B, which is isomorphic to 1. And I need to note that for n is not equal to 2, this case fails. It's not that. This doesn't work. If this is S1, of course the subgroup isn't, the fundamental group is not, the subgroup is not 1. In fact, the fundamental group of S1 or FS1 is 0, not 1. So this case only works for n greater than 2 or equal to 2. So only works. So no. N greater than equal to 2. Okay. So now, because these 3 spaces A, B, and C are path connected, we can apply Van Kampen. Van Kampen tells us that the fundamental group of Sn is isomorphic to the fundamental group of A, free product, fundamental group of B mod n, wherein that becomes the fundamental group of Sn is isomorphic to 1, free product 1 mod mod n. Well, n is this C here, and C is this section here. It could be C, but it could be some other subset that's not C, but kind of like C. And all that is just isomorphic to 1. Which is for some reason, well, n is isomorphic to 1. So this implies that pi 1 of Sn is isomorphic to 1 star 1 mod 1, which is isomorphic to 0. So Sn, the fundamental group of Sn is 0 for n greater than equal to 2. And just to femboyize it, just say Fsn, and then this is some subset, this is F instead of Rn. Fn, and then this is the femboy disk Fdn. So it's an enclosure, the closure of S1, or the interior of S1. And this is pi of Fs1, and then pi of Fs1, and the pi 1 of Fsn. So we just femboyized it. So there it is. Example 2. And okay, I talked about oh, we're already 10 minutes above the time limit. Okay, I will just discuss the next one in the next lecture. So I'll just do the remaining things, including what I talked about called presentations, right? So group presentations in the next lecture. And we're gonna, in the next lecture, at the beginning of it at least, we're gonna find the fundamental groups of Ft2, or Ftn, or no, T2, sorry, T2. And we will also find the fundamental group of an F sub 2 T2. And that I want to define that as the genus 2 femboid donut. So we're gonna find the fundamental groups of these two in the next lecture. So yeah, this is a good place to stop.